Well, greetings fellow Zibo fans. Today, in this first of what we hope is many training videos, we'll be covering the Center of Gravity CG program recently added to the tablet in the Zibo mod. So without further delay, we'll jump right into that. Now, on the home page of the tablet, in the top right corner, select the Weight and Balance icon. On the next page, select the Payload icon. On this page, you will note the payload, zero fuel weight, current fuel weight, the takeoff weight, and then at the bottom of the page will show the current centers of gravity. However, note that the landing weight CG may not show up until after the performance has been entered. As before, you can enter the fuel directly on this page. By selecting the payload at the top of the page, it will move you to the next page where you can enter a detailed payload summary. On this page, you can see here that the passenger zones are broken into 5 different zones, and we also have 3 columns that allow us to enter passengers directly in each particular zone. The total payload is at the bottom of the page. By selecting total payload directly, we can enter the total payload off of our flight planning software, and it will be automatically distributed by the Zibo mod. By directly entering cargo into either the forward or aft cargo compartments, you can easily modify and reconfigure the center of gravity to your liking, and this is a common process done by most airlines when they are trying to load the aircraft for optimum center of gravity. On page 3, we will find what is arguably the most important part of the weight and balance program. We'll find a graph here with our current center of gravity conditions overlaid on the graph, depicting whether or not the aircraft is currently loaded within the weight and balance limitations. On the left side of the page, you will find a summary of all the current operational weights. We begin with the basic empty weight at the top. The basic empty weight includes the basic aircraft as delivered from the factory, including equipment that is not removable, engine oils, hydraulic fluid, and all non-drainable fuel that remains on board the aircraft. Next, we will find the operating empty weight, or OEW, sometimes referred to as the basic operating weight. The OEW includes the weight of the flight crews, their personal baggage, and any work kits they may be carrying with them, as well as the cabin attendants, along with their personal baggage and cabin attendant kits, any additional equipment that's loaded on that's necessary for the particular flight, and also galley loading and potable water. These are examples of all the things we will find in an aircraft's operating empty weight, thus the difference between the OEW and the BEW in weight. Next in line is the ZFW, or zero fuel weight. The zero fuel weight is the operating empty weight plus the weight of all passengers, their baggage, carry-ons, and any cargo which may be loaded on board the aircraft. So that would become the total weight of the aircraft fully loaded with no fuel on board. This brings us to the landing weight, or LW. The landing weight is equal to the zero fuel weight plus any fuel that is remaining on board the aircraft at touchdown at destination. The landing weight is determined after the routing has been put in the FMS and the performance has been determined and initialized. Not shown on the page here is the ramp weight. The ramp weight is the total weight of the aircraft after the aircraft has been fueled and fully loaded. Finally, at the bottom of the page, we will find the TOW, or takeoff weight. The takeoff weight is the ramp weight minus any taxi fuel and APU burn which may have occurred prior to takeoff. This weight represents the weight of the aircraft at the numbers ready for takeoff. Once the airplane becomes airborne, the TOW will show up as GW, or gross weight, which is the current in-flight weight at any particular time during flight. One final note about landing weight. Landing weight is required by regulation to be determined and its center of gravity determined prior to departing the initial airport. So the landing weight CG is just as important prior to departure as it is on arrival. Now in this example, you can see that the landing weight just shows up as dashed lines. And as previously noted, this means that we have not yet completed the route programming and the performance programming. Now let's turn our attention to the weight and balance graph itself. Notice on the left column there is a weight scale. On the bottom there is a percent CG in Mach. On the forward edge or left side is the forward center of gravity envelope. And on the right side you will see the aftmost center of gravity envelope. Vertically, you will notice that at the top is the maximum gross weight the aircraft can have. Then you will also find the maximum landing weight that is permissible. These are structural limitations, by the way. And then the maximum zero fuel weight. The individual centers of gravity, as currently loaded, are depicted and overlaid on the graph itself. You'll notice at the top it shows that the takeoff weight center of gravity is very close to the top of the envelope. However, if the weight was beyond the maximum takeoff limit, you would see the TOW on the left side of the screen showing up in amber instead of white. In this example, you will also see that the zero fuel weight is shown as being below the maximum zero fuel weight line, indicating that this is an acceptable zero fuel weight load. And of course at the bottom is the original operating empty weight CG. Just to reiterate, the landing weight shows as dashed lines and is not illustrated in this example on the graph. And that is because the center of gravity itself cannot yet be determined for landing if we have not yet completed the route and the performance sections. On the right side of the graph, you will notice three slanted lines. These slanted lines represent the aftmost center of gravity that is allowable for a selected takeoff thrust setting. The leftmost line represents 26,000 pounds of thrust. The middle one is for 24,000 pounds of thrust, and the very right one is for 22,000 pounds of thrust. The reason for these limitations is that with an aft CG, there is a possibility that when you release the brakes for takeoff, that the nose may actually come off the ground and cause a tail strike. Not a good thing. So if you do find yourself on the right side of your selected thrust setting for takeoff, then you must select a lower thrust setting until the center of gravity moves forward of that line. If you cannot get it to move forward of the correct line for the particular setting, then what you will need to do is move your center of gravity by repositioning passengers and or cargo. Once we have determined the takeoff weight CG, we'll extract that number either from this page or page 1 of the weight and balance section and insert it into the takeoff page of the flight management system. This, of course, will allow us to determine the proper stab trim for takeoff with our takeoff weight CG. Finally, we come to the configuration page. Now, this is a great page because it allows you to customize your weight and balance for your particular needs. If you're flying for a virtual airline and they use particular passenger weights and or different configurations of galley weights, different passenger configurations, first class, business class, coach, whatever the case may be, you can modify it in this section right here. At the top of the page, we'll find 4 pre-configured passenger layouts. The default one is the one on the very left, 160 passengers, which is as the passenger layout in the Zibo mod is graphically and visually. You'll notice in this example that the high density maximum passenger configuration is what is currently configured for the weight and balance. You will note, though, that the graphic in page 1, which shows the various zones, will not change as of yet to illustrate the actual passenger layout, but you can control that passenger layout from this page. Beginning with the forwardmost zone, we will see the maximum allowable passengers in each particular zone moving from the forward end of the aircraft to the aft end of the aircraft over the 5 different zones. We will also see that we can configure individual passenger, flight attendant, and galley loads that are by default. In the left-hand column will be listed the maximums that you can use. The right-hand in green are the ones you can click on and modify to suit your own personal desire. They are currently set to a standard that is typical of most airlines and what are recommended by Boeing. Just to give you a tip about galley weights, typically these are set by sector for each airline. If you have a 1-hour flight sector, then they're going to have a standard galley load that probably doesn't include much more than some snacks and beverages. On the other hand, if you're on a 5-hour transcontinental flight, they may put 1 or even 2 meals on board for each passenger, plus snacks and beverages. So you can modify these galley loads as necessary for each type of sector that you fly, and that would be exactly what would be found on the airlines themselves. Finally, a discussion about flight attendants. How many flight attendants? As noted here, there are 2 flight attendants forward and 2 flight attendants aft. That's the standard for the 737, and it's all based on how many seats do we have installed. If the aircraft has 160 seats, it requires 4 flight attendants. If it has 189 seats, it still requires 4 flight attendants. Why is this the case? Because the regulations require that for each installed seating capacity of 50 passengers, there must be at least 1 cabin attendant. So from 150 to 200, it's going to be the same. 151, I should say, to 200, it'll be the same figure for cabin attendants. Whether sitting on the ramp, being under tow, or in flight, the center of gravity and its limitations play an important role in aviation safety. So just what is this all about? And what's the meaning of percent of Mach anyway? Well, let's take a little time to do a little primer so that you can better understand the importance of your center of gravity and its computations. First, let's begin with a little review of the aircraft's roll, pitch, and yaw axes, and how center of gravity and the various other forces in flight like thrust, drag, and lift all have an impact on how the aircraft flies. First, forgive my use of an Airbus since we're talking Boeing here, but this is a good graphic to illustrate. Notice that the roll axis, which is also the longitudinal axis, goes directly through the center of the aircraft from front to tail. The aircraft, when it rolls, induced by the ailerons, rolls about this axis. Then the lateral axis, also known as the pitch axis, is what is affected when we pull on the elevator or push down on the elevator or we change the pitch trim. Finally, we have the yaw axis, which is vertical, and this, of course, is affected by the rudder and or the yaw damper in flight. What is not illustrated by this picture is the fact that all of these axes run through the center of gravity. So when we roll the aircraft, we pitch the aircraft, or we yaw it, it actually moves or pivots around the current location of the CG. The center of gravity is exactly that. It is the concentrated location of all the mass in the aircraft, and if we were to hang the aircraft from a cable, it would balance exactly at the center of gravity point. Transport category aircraft are designed to be inherently stable provided they are operated within their center of gravity envelope limitations. When an aircraft has a forward center of gravity, it is more stable. In other words, it resists vertical displacement of the nose. When an aircraft is loaded with an aft center of gravity, on the other hand, it becomes less stable and more sensitive to pitch inputs. In fact, if it is loaded far enough aft, it becomes very unsafe. There are two types of stability that we're interested in. One is static stability, the other is dynamic stability. The three types of stability in static stability are illustrated well in this graphic. We have positive stability, neutral stability, and negative stability. An aircraft with positive static stability will tend to return to its previous dynamic trim point. An aircraft with neutral static stability, on the other hand, when the nose is displaced from its trim point, will tend, when the controls are released, to just stay in the current attitude that it's in. The worst case scenario is an aircraft which is displaying negative static stability, and in this case, when the nose is displaced from its trim point, the nose continues to diverge, either increasing in pitch attitude or decreasing in pitch attitude, which, of course, you could probably imagine is very dangerous. Dynamic stability is what occurs after an aircraft with positive static stability has a displacement of the nose either up or down. What we would like to see is what happens in example A here, where the oscillations, what we call phugoid oscillations, get smaller and smaller until the aircraft returns to its previous trim point. Now, the further aft that we load the aircraft center of gravity, the conditions tend to progressively move from A, positive static and positive dynamic stability, to B, neutral, and then to C, negative. An in-flight example of this would be I have an aircraft flying in level flight at 250 knots. I displace the nose up 10 degrees and then release the stick. The aircraft, if it's in positive stability, will go through a series of vertical oscillations, airspeed decreasing and increasing as the nose moves up and down, and eventually return to 250 knots in level flight at the altitude that it originally started from. In the case of example C, however, the aircraft may continue to oscillate further and further from the altitude and airspeed at which it started, ultimately maybe even resulting in a crash. This stability is the product of the relationship between the aerodynamic center of the wing, otherwise known as the 25% of Mach location, the center of gravity, and the neutral point. And the neutral point is something that is not shown on this diagram. Essentially, it is the fulcrum point where all the forces acting on the aircraft in flight come together as a fulcrum. Thrust, its pitching moment from thrust, lift, the downforce of the tail, any pitching moments caused by the fuselage, all come together at this point we call the neutral point. If the center of gravity is far enough aft that it's sitting directly on top of the neutral point, the aircraft will exhibit neutral dynamic stability. If it moves further aft, that's when the aircraft starts to show negative dynamic stability. Now, Boeing doesn't tell us exactly where this neutral point is located. Instead, what they do is they give us the center of gravity envelope, define its aftmost limit, and tell us not to operate the aircraft behind that limit. In this particular case, the aftmost limit possible is 36% of Mach. Now that brings us to our final subject in this tutorial. What is Mach? Mean aerodynamic chord. And what does it have to do with center of gravity, and why is it so important in the first place? When we consider a straight-wing aircraft, its aerodynamic center, or center of lift, is in a consistent point 25% aft of the leading edge of the wing. However, it gets more complicated when we look at a swept-wing aircraft. As you can see by the illustration, the swept-wing aircraft, its aerodynamic center on any given point on the wing moves aft due to the wing sweep. This makes determining where we need to put the center of gravity in relationship to the aircraft much more difficult, because where is the center of lift anyway? On a straight-wing aircraft, we merely measure the distance from the front of the wing to the trailing edge of the wing, and that is the length of the chord. The quarter chord, or aerodynamic center as it is also known, is very easy to find in this case. However, with the swept-wing aircraft, the quarter chord moves aft along with the sweep and taper of the wing. What we need to do is mathematically convert this swept wing to a straight wing, and that'll solve our problem. Fortunately, the engineers at Boeing have done this for us, and the leading edge of Mach is located 627.1 inches behind the reference point for center of gravity purposes, and Mach is a total of 155.8 inches long. Interestingly, you'll note by this diagram that the leading edge of Mach does not start at the wing root, and it does not end at the trailing edge of the wingtip. It's an average. The basic center of gravity formula locates the CG in inches aft of the reference point near the nose of the aircraft normally. Once we know the mean aerodynamic chord, where it begins and where it ends, we can then use a formula to convert the center of gravity to a CG in percent Mach. Well, I hope you enjoyed this presentation. I hope I didn't confuse you too much with my final explanation of how weight and balance works. We didn't get into the formulas. We don't need to do that. But at least I hope now you have a basic understanding of how center of gravity and the mean aerodynamic chord are related to each other. So I hope you enjoyed this video. We'll do more of them, and looking forward to seeing you again soon. Now I've got this takeoff challenge. Gee, I've got a full airplane, full tank of gas, going to Honolulu out of Santa Barbara. Boss says if I don't take this trip, I don't get my bonus. So, gee, it's a pretty short runway. I wonder if I can make it. I hope I can make it. Well, let's see what happens. 6,500 feet of runway. That's pretty short, but well, let me see. I got flaps 25. I'll do a max static takeoff. I think I'll be okay.
Flight attendants, please be seated for departure.
Positive rate.
Man, that was really close. I hope I don't have any scrapes on the belly, because there'll go my bonus. Man, I'm really looking forward to Zibo finishing that takeoff performance section, so we can do a video on that. Take care, folks. Have a good day.
1,000.